Jai Jagannath friends, this is our third lecture on topology. Let X be a set and tau be a collection of subsets of X. Tau is said to be a topology if it satisfies three conditions. We have already discussed this. Tau is said to be a topology if it satisfies three conditions. First one is that phi and x must be elements of set tau. Phi must be an element of the collection tau, and the set x itself must be an element of the collection of the subsets, the family of subsets. Second condition is that any union of elements of tau must belong to tau. Third condition is that any intersection of finite elements of tau is an element of tau. Any intersection of finite elements of tau should belong to tau. If all the three above conditions are satisfied by tau, then it is said to be a topology. Let us examine, friends. Let X is equal to 1, 2, 3 be a set, and let us consider some collections of subsets of X. We need not to write all the subsets of set X. We have already studied. Let us take some collections. Let one collection be phi 1, 2, 1, 2, and 1, 2, 3. We shall call it tau 1. Tau 2 is 1, 2, 1, 2, 1, 2, 3. This is the second collection. Tau 3 is phi 1, 2, 1, 2. See, all the elements of these sets are subsets of X. Tau 4 is, let us take phi 1, 2, 3, 1, 2, and 1, 2, 3. Let tau 5 be 1, 2, 1, 2. These are 5 examples of collections of subsets of set X. Here let us examine the conditions, friend, and let us see which one is topology and which are not. Let us consider first about the tau 2. See, friends, in tau 2 there is no phi. So tau 2 is not a topology. Why? Because the first condition is not satisfied. Phi does not belong to tau 2. Condition 1 is not satisfied. Tau 3 let us examine. This is also not a topology. Why? Because you observe, friend, X does not belong to tau 3. There is no X or the set itself 1, 2, 3 here. So tau 2 is not a topology because X is not an element of tau 3. So condition 1 is not satisfied. Similarly, let us examine, friend, tau 4. What about tau 4? Here phi exists, set X exists, but the second condition that the union of any two elements must belong to the set. Here observe, friends, that let us consider these two, 2 and 3. And what is the union of 2 and 3? 2 and union of 3 is equal to 2, 3. But this 2, 3 does not belong to tau 4. Hence, tau 4 is also not a topology because union of 2 and 3 is equal to 2, 3 is not an element of tau 4. So condition 2 is not satisfied. Hence tau 4 is not a topology. And what about tau 5, friends? See, tau 5 is also not a topology. Why, friends? Because you see, these are the elements 1 and 2. And what is their intersection? Intersection of 1 and 2 is phi, obviously. But this phi is not again an element of tau 5. So condition 3 is not satisfied. Also condition 1 is not satisfied, that phi does not belong to the set. I have taken just an example to clarify you. Here the condition 3 is not satisfied. Hence tau 5 is also not a topology. What about tau 1, friends? See, let us examine. Here phi set belongs to the set X itself belongs to the set, and we may verify that any union or intersection of the sets also belong to the set. Hence it is a topology, because you see, friend, phi union 1 is 1 exists, phi union 2 is 2 exists, phi with any union of any set is the set itself, the set exists, and intersection of 1 and 2 is phi exists, intersection of 2 and 1 2 is 2 exists, intersection of 1 and 2 is 1 exists, intersection of 1 2 3 and 1 2 is 1 2 3 exists. So we may examine that union of every elements and intersection of every elements belong to the set. Hence condition 1 is satisfied, condition 2 is satisfied, condition 3 is satisfied. Hence friend, tau is a topology. Thank you, friends, for watching this video.